Now, today we are going to start with the oscillations. Simple harmonic motion is also called as SHM, is an oscillatory motion in which the force acting on a body is directly proportional to the displacement. If you see the equation here, F is the force acting on a body is directly proportional to minus x, where x is called as displacement. A negative sign indicates the direction is opposite. The displacement of the direction displacement is opposite. Therefore, F is equal to minus kx, where k is called as a force constant. Simple harmonic motion can also be defined as motion which represents itself at regular intervals of time. Examples of simple harmonic motion: oscillations of a simple pendulum, a swing in a park when pushed once, and oscillations of a balance wheel of a wristwatch and a mass loaded spring when it is pulled down. If you see these examples of simple harmonic motion, the oscillations of a simple pendulum can be treated as a simple harmonic oscillations. What is happening when the bob is tied to a thread, and if you give a small displacement by applying a force, it is set into oscillations. So these oscillations are called as simple harmonic motions. Now it is going to and fro, that is from the mean position goes to an extreme position and comes back to the mean position, again goes to the extreme position, and the cycle goes on. For examples, a child sitting in a swing in a park, and when you push once, it keeps oscillating to and fro until the external force is been applied. It is moving, and as long as the force is required because of the frictional force, it is coming to rest. Oscillations of a balance wheel of a wristwatch and a mass loaded spring when pulled down, it is set into oscillations, and the oscillations we see in a mass loaded spring are also simple harmonic oscillations. Next we go with the characteristics of a simple harmonic motion. Simple harmonic motion is a special case of a periodic motion. Simple harmonic motion system must have a mass and hence inertia. In simple harmonic motion, a constant restoring force always acts on a body. In simple harmonic motion, the acceleration produced in a body due to restoring force is directly proportional to the displacement of the body from the equilibrium position. In simple harmonic motion, the direction of acceleration or the restoring force is opposite to the displacement. Simple harmonic motion is represented by x is equal to a sine omega t, where x is called as a displacement, a is called as amplitude, omega is called as angular frequency, and t is at any instant of time t. If you see the characteristics of simple harmonic motion, you can see it is a periodic motion and it requires a bob, like oscillations in a simple pendulum. It requires a bob which is moving to and fro, and always a force acting on it and a restoring force. What is meant by a restoring force? Restoring force is a force that is developed in a system which opposes the external force. If you see in the case of a simple pendulum, when you give a small displacement, it moves to and fro. Once it goes to the extreme position, it comes back to the equilibrium position or the mean position. That means the bob is forced to come back to the mean position. That force which is coming to restore to its original position is called as a restoring force, and this restoring force is directly proportional to the displacement of a body from the equilibrium position. Now, what is meant by acceleration and the restoring force? We know what is the relation between force and acceleration. F is equal to ma. When the force is opposite to the displacement, similarly F is equal to ma, therefore A is also opposite to the displacement. And we see that simple harmonic motion is represented by x is equal to a sine omega t. Now we are using a sine function because a sine function is nothing but if you start from 0, it reaches to maximum in a sine wave and again comes back to the 0, and it goes to a negative peak, again comes back to the 0. So one complete cycle is a sine wave. So even sine wave and cosine wave, both these waves are taken to be examples of simple harmonic motion. Therefore, we are taking cos function and sine function as a simple harmonic motion, which is nothing but we are going to derive the equation now. Differential equation of motion for a simple harmonic motion. So using the sine function and the cosine function, we are going to develop a differential equation for a simple harmonic motion. Let the body is initiated to oscillatory motion after being displaced from the equilibrium position and left free. Mean position is a center position and equilibrium position is nothing but a mean position. And the extreme position, that means it is going displaced to certain amount and coming back to the equilibrium position, that will be the displacement. As said earlier, restoring force is equal to minus kx, where k is called as a force constant. F restoring is equal to minus kx. F is equal to ma as per the Newton's second law. F is equal to m into a. A is nothing but the acceleration. We all know that when x is a displacement, dx by dt gives the velocity and d square x by dt square gives you the acceleration. So substituting that value as a in F restoring is equal to minus kx, m is equal to d square x by dt square is equal to minus kx. So rearranging the terms, d square x by dt square is equal to minus k by m into x. Bringing the minus term to the left hand side, d square x by dt square plus k by m into x is equal to 0. This equation 1 is called as differential equation of simple harmonic motion. So this equation 1 is called as a differential equation of a simple harmonic motion. Now we as said earlier, the solution for the simple harmonic motion is given by x is equal to a sine omega t, which is nothing but equation 2. As discussed, sine functions and cosine functions are nothing but a harmonic function. So we are taking that as a solution for the equation 1, where a is the amplitude, omega is the angular frequency and t is the time lapsed. Since x is a displacement, dx by dt gives you the velocity. So differentiating equation 2 with respect to time, dx by dt is equal to a omega cos of omega t. And again, differentiating again with respect to t, d square x by dt square is equal to minus a omega square sine of omega t. We all know the differential of cos omega t is minus sine omega t. Therefore, there is a minus sign over there and omega square because the two omegas have come into picture. So we can write the equation as d square x by dt square is equal to minus omega square into a into sine of omega t. We already discussed that a sine omega t can be taken as x. So a sine omega t is represented by x. And rearranging the terms, you are getting as d square x by dt square is equal to minus omega square into x. Bringing the negative term towards the left hand side, we get it as d square x by dt square minus omega square into x is equal to 0. This is called as equation 3. Now comparing the equation 3 with equation 1, where we have got it as d square x by dt square plus k by m is equal to omega square is equal to 0. So k from equation 3, that is from equation 3 and equation 1. If you see that equation 1 is k by m here and equation 3 is omega square. So comparing 1 and 3, we are getting as k by m is equal to omega square. So it can also be written as omega is equal to root of k by m. For a body executing free or undamped vibrations, its angular frequency of vibration omega is called as a natural frequency of vibrations of a body. Now here k is the spring constant or the force constant, m is the mass. The relation between the natural frequency and the force constant is given by omega square is equal to k by m. The time period of oscillation is given by t is equal to 2 pi by omega. Since we have the relation as omega is equal to 2 pi f and 1 by f can be taken as t. So we get it as t is equal to 2 pi by omega. Substituting the value of omega into this t is equal to 2 pi by omega, you get it as 2 pi into root of m by k. So the time period of oscillation is given by t is equal to 2 pi into root of m by k, where m is the mass of a spring and k is the spring constant or the force constant. Now the important thing that you have to see here is the relation between the force constant and the natural frequency. K by m is equal to omega square. This is what we have derived in this first order differential equation. This is the equation for a simple harmonic motion, and we have derived the time period of oscillation as t is equal to 2 pi by omega, that is 2 pi into root of m by k. Thank you.